Hi everybody, we're the MechEng defectors. And so our project was the housing dataset, and we wanted to look specifically at the NOx aspect. You could have chosen to analyze the price or the NOx levels. We picked the NOx. So my name's Giriagos. I'm a fourth-year MechEng student.
And I'm Yusuf, also a fourth-year MechEng student.
Great. Okay, so what we did first was that we wanted to have a look. So our project in general was to analyze sort of the NOx levels that we can see in Boston based on the socioeconomic level of based on the socioeconomic level of the housing data that we had. So our first task was to separate the data into 3 clusters, which indicated socioeconomic class. So we did some analysis. We found that 3 was the best, the optimal amount of clusters. So you can see that we have 3. We have red, orange, and yellow, and the red is of the lowest socioeconomic status. So the poorer areas, the rougher areas with the most crime. Orange is somewhere in the middle, and yellow is the most affluent, the richer areas. And once we did this, we had separated each sort of data instance assigned it a cluster. We wanted to analyze the NOx levels.
The next step was naturally, since we were predicting NOx levels, was to create a regression model that could actually predict the NOx levels. And what the flowchart on the left is showing in very simple terms is our methodology for choosing the best model, which was starting with a benchmark model, so like a linear regression, and then going through it, changing parameters, finding the scores, and seeing how we could improve it by changing the model or even changing parameters of the model that we're using. From this, we found that SVR was the best model, and this made sense with our assumptions as well, because one of the attributes that we were using was RAD, which is actually an ordinal index, and therefore represents, I guess, an abstract form of distance, and therefore is more like a categorical variable than an actual continuous one, which is why SVR had a much higher accuracy. Next slide, please. So after that, what we then did was we wanted to determine what the marginal effect of changing one parameter would have on the entire predictions of NOx. And we focused this analysis on the parameters that weren't actually geographically constrained, which were actually socioeconomic ones, and this includes age and crime. So the reason why we did this is because in terms of implementing policy change, it's very difficult to say that we're going to change the location of the low-income areas, because that's not really a feasible outcome in a very short amount of time, which is why we wanted to explore what the effect of changing, say, socioeconomic variables has on the NOx. So for example, the first graph on the left shows how changing age while keeping all other variables constant affects NOx. Next slide, please. The final step was actually trying to simulate what the developing low-income area is. And what this really means is how can we change the low-income dataset in a way that makes it similar to the high-income dataset. And to do this, what we did is we replaced the non-geographically constrained parameters, which would be the socioeconomic ones, with that of bootstrapped variables from the high-income dataset, thereby simulating improvement. The graph on the left shows the low-income data points before the improvement, and on the right after the improvement, showing a significant decrease in NOx. Next slide, please. So the insights that we gained were that uplifting low-income neighborhoods do lead to lower NOx levels, and that increasing crime or house age, all other things equal, increased NOx levels. Now, this was a bit surprising to us because it doesn't seem, those don't seem like things that would necessarily cause that change, which is why, next slide please, one of our recommendations for future work is to explore the causal relationship between those two socioeconomic variables. So would changing crime in an area, for instance, cause a decrease in NOx levels, or is it more a correlative behavior? Next slide, please.
Oh, sorry.
Oh, yeah, well, thank you very much for attending and watching our presentation.
Okay.
And we're happy to take any questions that you may have.
Yeah, so here we have like a Q&A session from the judges. So we have a video here from Imperial. We also have Brian Liu from ASOS and Imperial. We have also Liz Todd from Microsoft. We have Ashton Martin from the Accenture. And we have Shasha from Kaiko. Yeah, any question from the judges to this team?
Yes, I have to say, superb use of GitHub and documentation. I've just been looking through it as you've been presenting. So I've only literally seen 4 minutes of documentation, but it looks very, very good, very extensive. In terms of your next steps, how could you see this being taken forward?
Do you mean in terms of policy changes or the work itself?
In terms of the work itself.
I think one thing that we'd be interested in is to actually explore the causal effect of the parameters that we can actually change, because we're not entirely convinced that, like, for example, crime will lead, like a decrease in crime will lead to a decrease in NOx, just because that doesn't really make sense in terms of, I guess, intuition. We think that's more of a correlative parameter, so that if you implement policies that would end up decreasing crime, if then crime decreases, then you can say that, oh, we expect NOx to decrease. So yeah, the first step would be looking into causal effects of those parameters.
Okay, and you feel you had sufficient data in the data set to build a causality model, or would you feel you needed more data to build that model out?
We're not sure. We'd have to look into it.
Okay, great. Anybody else got any questions?
Hi there. Great work. Do you want to speculate why crime and NOx may be correlated in this case? Just throw out any ideas.
Yeah, if I could answer this one. So we didn't show this in the presentation, but we had sort of a map of Boston that we found online, which we were comparing to, which actually showed socioeconomic levels. And from what we can gather, the lower income areas are, you could see from our cluster plots that they're closer to the center of Boston. And the reason for that is because there's a lot of industry in the middle of Boston. So we were assuming that the less affluent areas would be more sort of working class and working in industry. And so they would be living close to the industrial areas. And also because the houses were quite old in that area, it seems like quite a rundown neighborhood. So generally, because it's a very sort of industrious area and it's not as affluent as the sort of suburbs, we would expect there to be higher crime there, because that sort of everyone just that's where sort of the poorer people just live closer to the industry, and it's the industry that is causing the biggest output in NOx. And so I think that's the sort of the correlation between crime and NOx. It's more sort of that the areas of higher crime are closer to the areas with a lot of industry, which are producing the NOx. That was sort of the conclusion that we came to from looking at our sort of results.
Yeah, that makes sense. Thank you.
Thank you.
Hello, Kyriakos and Youssef. Thank you very much for that presentation. Martin here, Martin Ashton from Singapore. That was a very nice presentation. I enjoyed listening to that, and this curious relationship between NOx levels and affluence. It does remind me of the kind of a spurious correlation they found between ice cream sales and homicides. And of course, the confounding variable there is temperature. As the temperature goes up, so more people have ice cream and more people commit crimes. So there we go. It might be something like that. I think I like your explanation of it even better. So thanks for that. Really, really nice presentation.
Thank you very much. I'm
Thank
glad you enjoyed it.
And hello, Sasha from Kaigo here. Yeah, thanks a lot for this great presentation. Don't have much to add in terms of questions. I think you did a great job, and the website is very intuitive. I sent in the chat a little link to a paper that was written a couple of years ago on the Chicago dataset that I think you might find interesting as well.
Okay, thank you very much. Thank you. We'll definitely have a look at that.
Okay, so maybe the JARL can prepare to present. Thank you so much for making it vector. I guess it was a really great presentation.
Thank you.
Thank you very much. Thank
And
you.
then for the JARL, maybe can sharing your screen.
Yep. Can you guys see my screen?
Yep. Your time start whenever you're ready.
Yep. Give me a second, sorry.
You guys ready?
Let's do it.
Yeah, you have 5 minutes from now.
Okay. Good morning. We're Tim Yao, and we'll be talking to you today about regression and spatial analysis of the Boston housing market.
So the Boston housing dataset is one that's widely known and has been used in many studies since 1978. And we took the data from Gilly and Pace and decided to remove any categorical data and the redundant median and valley feature. We also checked the dataset for any nulls, but none were found. After cleaning the data, we decided to inspect the target variable, which in our case was the corrected median value of the houses, and we plotted its distribution. As you can see in the graph, it pretty much follows a Gaussian distribution with mean of 22K and standard deviation of $9K. There is a considerable anomaly at 50K, but that is due to the fact that in the dataset, the house values are capped at 50K. We then decided to plot a correlation matrix between the features to see if there were any interesting linear relationships, and we found some of them. For example, there's a high correlation between RAD and tax, so houses closer to highways tend to have a higher tax rate, but when performing this kind of analysis, we should keep in mind that correlation does not necessarily imply causation.
So we initially opted for a random forest as research has shown it is well suited for this type of task. With our initial base model, we got an R-squared score of 0.9. After a randomized grid search, the optimal solution used 13 trees, giving an R-squared scored of 0.91. We found that the most important features used to predict the house prices were RM, the number of rooms per dwelling, LSTAT, the percentage of lower status of the population. This means those without high school education and those classified as laborers, as well as distance to 5 Boston employment centers, crime rate per capita, and NOx, nitrous oxide concentration. Now, some of these attributes like the location and number of rooms can directly contribute to the house price, whereas some instead result from the house prices. For example, those that can afford it prefer to live closer to work, hence this is important. Also, studies have shown that lower house prices correlate to less crime, hence crime is important.
And the second approach we had was a deep learning approach. And we know that neural networks historically perform quite poorly on tabular regression tasks where you have a small amount of data and a fewer samples. And in an attempt to improve the accuracy of these predictions, we needed the model to really look past the noise and to effectively learn the underlying relations, and to do this in a data-efficient manner. And so we decided to utilize an autoencoder and to squeeze the inputs into a more concise latent space, capturing the essential degrees of freedom. And then from this latent space, a shallow MLP was trained to map this to the true housing prices. And so from our analysis, it was seen that adding the upstream encoder did actually increase the accuracy of the model, returning an R-squared of 0.88 over the base model of 0.82, which was just with an MLP network with identical hidden layers and the same input data, thus showing a clear improvement.
Now towards the spatial analysis of house prices. The heat map to the left shows the concentration of very high value housing, which is mostly outside the city, while low value housing is near the city center. But according to the Housing Assistance Council, in 2016, this distribution is similar in and out of Boston. Let's go to the next point. There it goes. And this is most likely to be an effect of house price increases even after adjusting for inflation. Now, a close-up view of where these areas are. Richer places are near green areas or wealthy areas such as Beacon Hill and Back Bay, while the less valuable areas are near industrial places or where socio-economic unrest was happening, leading from the desegregation of public schools in the 1970s. Next slide, please.
And so finally, to interpret the results that we've collected, despite all the data being Boston specific, we were able to obtain general insights into the housing market and what features most influence the value of a home. Also, looking at spatial analysis, a long-term housing investor should look towards the low-value city centers, as prices will significantly increase to have a good return on investment. We've also seen that NOx is generated by richer neighborhoods, but impacts on poorer areas. So the city should opt for social change towards emissions instead of technological. And overall, both our random forest and our autoencoder multi-layer perceptron models gave accurate predictions of the house values, with the random forest performing slightly better as expected. And for future work, something we thought we would try was to determine several town center coordinates around Boston, so different town centers, and to create radial vectors to each house. And to normalize and use this as an additional feature.
Okay, thank you so much.
Okay.
Thank you so much, your team. So we will give you a reminder at the 4 minutes mark on the team chat, and then the judges will have 3.5 minutes to ask questions. And now, yeah, I will let the judges ask the questions.
This is Ovidio from Data Science Institute at Imperial College London. I just have a quick question. Why did you decide to remove or ignore the categorical labels from your data set?
Do you have a... If nobody's got... Okay, so I can answer that. We first of all saw that in our data exploration, when we looked at the sort of importance at different variables, we saw that categorical labels didn't seem to show up as important as we thought. And so we did exclude them. We did try them in our models initially just to see where it would be, and removing them didn't seem to have very much impact. And so just for reducing the dimension of the problem, we decided to remove some features, and we thought that those would be the good features to remove.
Okay, thank you.
And also the town number and town name data was also kind of included in the longitude and latitude data, which we use.
Hi there, a question from me. So you mentioned that you did a comparative analysis between when the Boston data set is made, the 70s and 2016, and found that the insights actually, things has changed a lot since. What do you think if you were to extend your work that you will have to do in order to confirm or or reject this hypothesis?
I can answer that. So it's in our future work to try and obtain similar data for Boston in the present day and compare. So what we're most interested in is trying to sort of get a lot of different data sets and then merge these data sets together based on the most important features that we found in the earlier analysis. So I think our plan for action for that might be just to search for a lot of different data sets, pull out the data that's probably most important, and perhaps try and map it, and also run the feature analysis again to see if the importances have changed since then.
Cool, thank you.
Hi team. So yeah, great presentation again. I think what you did there was prove a lot of known knowns. So in terms of where residents and prices are based. So in terms of low income inner cities, high income rural areas. Did you do any analysis into the predictions of where low income families could live in the future? You talked about investment into inner cities, which are currently low based areas, but did you have any considerations about where do these low income families end up living if the price of the residential area goes up within an inner city? So, there's been massive issues in Seattle, there's been massive issues in New York. Did you look at any of those sort of questions?
I'm afraid we didn't quite look into where the low economic families would be living. Are you talking about in the future? Or...
Yeah, in the future, yeah. So in terms of prediction, so you predicted that these areas are good investment areas from an acquisition or property purchase perspective. But if you're pushing people who are low income out of the city centres, where are they going to end up living, or where are the predictions of where they will end up living?
Yeah, I don't think we've considered that.
Yeah, it's a huge issue worldwide. Look at Seattle, San Francisco, New York, even in the UK now. So,
all right, we'll do that as part of our future work, I think. So,
okay,
thank you very much.
Yeah, all right. Thank you so much. Was a great presentation. And then we can move on to the next team, which is Bandicoot. Are Bandicoots here?
Yes, we are.
Yeah, you start sharing your screen. Yeah, whenever you're ready.
So hi everyone, I'm Jemima. I'm a first year PhD in electrical engineering, and this is Travis, my flatmate. He is a third year PhD in mechanical engineering, and we focused on trying to predict housing prices, and we wanted to see the effect of reading in information about the locations of hospitals, schools, universities, train stations, and community health centres, because these are all things that you might see on a real estate website for evaluating whether you want to buy a new home. So we read in that data. One thing to be conscious of is the data we read in is data from the last 6 years, because that is readily available online, but the Boston housing data set is from the 1970s. So really we're assuming that the facilities in the area haven't really changed over the last 40 to 45 years. So looking into that a bit more will definitely be something for future work, but we think it's a good enough approximation given the time constraints, because a lot of the facilities we're looking at are very long standing. So for example, universities and hospitals could be an area for decades, if not centuries. Then we checked and cleaned the data, and the data set we got was really lovely and clean, but we still ran quite a few checks on there. Another couple of important points to note is that we were trying to predict the C MEDV column, so we needed to drop the MEDV column because otherwise we'd have data leakage, because the C MEDV column is just the corrected MEDV column. So if you have that in your feature data, you're going to get overly optimistic results. And we also dropped the town column with all the strings of town names, because that information is repeated in the town number column, which gives an ID to each of the towns. One of the first things that we did was visualize the geospatial data on a map, and you can see that we have lots of icons representing schools, hospitals, universities, etc. And we also have these little colored points here. And these coloured points are the houses, and they're coloured according to the town that they're in, because we just wanted to get a sense of like what information the data set was giving us. We then used the information we pulled in about all the different facilities to calculate the distance to the nearest of each facility. So the nearest school, the nearest hospital, university, nearest train station, and nearest health centre. And we created new features that way. We also created new features a second way by having a 10-kilometre buffer, a 10-kilometre radius around each house, and counting the number of each utility that fell within that. We have the distribution of each of the distance to the nearest of each facility here, and this is the count for each of the facilities within 10 kilometres. You can see that it's quite skewed, but we do normalise the data, so we're not too worried about that. And then we also looked at the mutual information score to tell us which of the features give us which of the features reduce the uncertainty in the target variable the most. And we can see that 2 of the features that we've actually created about health centres make it into the top 10 that we'll use later in our best performing prediction model. We also made a correlation matrix, and we did a principal component analysis to see how closely correlated the different features were, but unfortunately, due to time constraints, we didn't have time to incorporate our findings there into our actual models. So now onto the regression models. We used 5-fold cross-validation in order to evaluate our models. And we used our linear model as a benchmark. We also looked at using an elastic net, and this linear model and the elastic net and the third row here, the decision tree regression, these are all on the full data set because we just wanted to see what would happen. And you can see that the decision tree regression performs the best, potentially because it's picking up on some nonlinear trends, which the elastic net and the linear model ignore. Then we used a feature selection, our top 10 based on mutual information score, and just fed those into the decision tree. And we see that it performs much, much better overall. Now, potentially there is a problem with the overfitting with the decision tree. We can see that it performs much better on the training sets. That's something we need to consider. Even though we did a search for hyperparameters to do with the penalty, potentially we need to, we did a hyperparameter search to do with the pruning of the trees. We potentially need to do a hyperparameter search for the maximum depth as well, and that would help to resolve that problem. But overall, those are our results. We find that introducing information about the health centres and selecting only features within the top 10 based on mutual information
Okay,
score.
fantastic. Thank you so much. And let the judges take control and ask questions.
Hi there. It's interesting an idea, which is totally sensible that you include like amenities into the area, maybe as a parent or as a student, or as everyone will be interested in whether their neighborhood has good facilities. I just want to see if you guys have thought of try to quantifying the impact of like having 5 health centers in my neighborhood and what the premium of that is to the house price. If not, any approach in doing so.
We haven't quantified it yet, but I think that would definitely be a good step for future work, looking into the exact trend between the health centres and the median house price. Do you have anything? Yeah, I think, yeah, that would definitely be really interesting and definitely be something we'd like to do, but unfortunately, due to time, we couldn't.
Yeah, I think a lot of it was just due to time. There was a lot we wanted to do.
Yeah.
Any other questions?
Yeah, this is Martin Ashton again from Singapore. Thank you for that. That was a lovely presentation. I have to teach a class to my team, which is about how to use data to drive consulting. And it's a big subject. It's huge. And now many companies are now moving towards this. And so it's all about how do you extract your data, how do you process the data, filter it, visualize it. But then I put a big emphasis on the storytelling, because that part is the most important part in the business world, being able to tell a nice story. And I like the story you were telling. It's very coherent and it made a lot of sense. I like the visuals as well. Normally sort of going through the code, I know Python allows this visualization, so it's great, it's fine. One thing I was thinking of was VIF. Have you heard of variance inflation factors? And this might be everybody actually.
No, I haven't.
It's okay if you haven't, it's fine. It's a useful measure for removing variables which may have correlations already with other variables. So it allows you to remove overweighted variables from your data sets. So sometimes variables can appear in different columns or different features a number of times, and that can then skew the results at the end. So I was looking at your correlation matrix very briefly, and I understand you've created some of your own features, which was very nice, excellent. But just as a final check, it's good to run VIF against all of that, just to filter out, just in case there's other duplicated parameters in that, duplicated correlations.
That makes sense. Thank you. Thank you for letting us know.
You're welcome. All the best.
Yeah, so I was going to just briefly, touch on what Martin was saying as well. I think, your analysis is good. I like the way you've looked at different models. And one of the questions I had was, did you do those models manually, or did you use something like AutoML to predict which the best algorithm should be for the data sets? And again, AutoML contains VIF, etc. So it would have done a lot of the correlations for you.
I'm sorry, is the question, how did we select the models we used?
Yeah.
So we didn't use anything like R2ML, we just used our experience, and we thought linear regression was the most basic model that we could do. So we decided to use that as our benchmark. We know that ElasticNet can, because of, I think, the lasso component, it's almost like doing feature selection itself. So because that's partly what we're doing, we thought we would try using that model. And we knew that the decision tree regressor could pick up on some of the non-linear trends that the linear model and the ElasticNet might ignore. So we decided to try that. But could you repeat what you mentioned that could help us select those models? Because that sounds very interesting.
So there's a tool set called AutoML. So within like Azure and Google, and I think Amazon also have it. It's an actual feature within the machine learning services products, which basically you run your data set against. It will run every single algorithm and tell you which the predictors and the model outcomes are for each of the algorithms. So it rapidly increases the speed at which you can start to build models and then understand which technique to use best.
Oh, fantastic. Thank you so much for letting us know about that.
Excellent. So yeah, great presentation again.
Thank you.